Hey everybody, so here's a brand new topic on angular momentum. So just to bring things into context, let's say, recall, if you have some object here, subject to some force, and I say, what is the torque about a point over here? Let's call this point A. The torque about point A due to that force F. It would be like this. Right? The torque would be R cross F about point A. Okay, so very similar to that. This time imagine you have some mass here, and then it has momentum. So this is the momentum, right? Mass times velocity. That's linear momentum. Now we're introducing something called angular momentum. So say, what is the angular momentum? L, so this is angular momentum of this object about point A. It would be just like this. R cross P, the momentum. So this is angular momentum. For this example, about point A. Okay, so that is for a single particle. What if instead you had a bunch of particles? Right, then you would just add them all up, sum, but then imagine if it were a rigid body, like a disk, like this. See, you basically add up the angular momentum for every single molecule in this rigid body. And I'll just tell you the answer. So it would be, so this is for a particle. And then for a rigid body, it would be I omega. Just like it's the same proof that when we did torque. If you add them all up, it's I alpha. So just like that. And these two actually are related because the truth is Newton's second law, that I just wrote there for rotation, some torque equals the time derivative of angular momentum. Okay, so this is angular momentum. This is for a single particle. This is for a rigid body that has a moment of inertia, I. Okay, so where you know the moment of inertia. And this is Newton's second law for rotation. If you just substitute that, I omega, right? Then let's assume the moment of inertia is constant for this particular example. Then d omega dt. What's the time derivative of angular velocity? Angular acceleration. Right, so that's how we started off Newton's second law for rotation. Now that you know angular momentum, it's like this. All right, so that's Newton's second law for rotation. And if you have no net torque, if that's zero, if this is zero, that's the same thing as saying L is constant, right? If the time derivative of something is zero, then that something is constant. Or another way to say it is conserved. Compare that to Newton's second law like this. If you have no net force, so if this is zero, right, the time derivative of P is zero is the same thing as saying P is constant or conserved, right? So look, that's conservation of linear momentum, conservation of angular momentum. So it's analogous to everything we did with linear momentum. Okay, how about a concrete example here? Let's say you have a let's start with a simple conceptual. So let's say there's a figure skater spinning with arms outstretched like this, so kind of spinning around with some initial angular velocity. And there's no person coming along applying torque to the figure skater. So the figure skater has some moment of inertia initially. So what happens when the figure skater does this? Right, so then the moment of inertia is now different. So initial and final are now different. So what happens to the angular velocity? So if angular momentum is conserved, angular momentum initially, then it's the same final, right? So this is conservation of angular momentum. Initially, I omega. Final, I omega. So if your arms are outstretched like this compared to like this is larger, this is smaller. So if this is larger, and this is this should be final, is smaller, then that means this has got to be smaller, the initial angular velocity, and final has to be larger. Right, so you're going slower and faster over here. And this would be different if somebody came along and applied torque to the person. In this case, there's no torque. There's no external torque here. That's why this is 0, which is why angular momentum is conserved. Okay, so this is kind of the introduction. I'll save another example for its own video, so stay tuned for that one. See you in the next video.